Hello, everybody. Welcome back. In the last few videos, we looked at how to study the relationship between two quantitative variables by using scatter plots, and then we looked at the correlation coefficient, which is the measure of the linear relationship between two quantitative variables. In this video, we will now focus on the regression line, and which I'm going to define in a bit. But before I do that, let me recall two facts. So from analytic geometry. So let's say So let's say that we have this horizontal axis and the vertical axis. The horizontal axis represents the variable x, and the vertical axis represents the variable y. Let's say that xy is a so let's say that xy here are the rectangular coordinates of this point. Then notice that the y coordinate here is the height of the point from the horizontal axis. That is, the y coordinate of the point is the distance from the point to the horizontal axis, and the x coordinate of the point is the distance from the point to the y axis. Now we have, so here let's say the equation of a straight line it always has the following form. So y hat is equal to b0 plus b1x. So this is called a linear equation where b0 and b1 are constants. So basically, if I pick a point x along the horizontal axis, then the corresponding y hat value is the height of the line at that x. And here b1 is called the slope of the line, which measures how steep the line is with respect to the x-axis, and b0 is the y-intercept. That is, b0 is the y-intercept. Basically what it means is that b0 is the point where the line crosses the y-axis. So this point right here, that's b0. Okay, so let's say that I have a scatter plot with 4 points, and I'm picking only 4 points for simplicity so that I don't have to draw too many points. And to have some interpretation in our mind, let's say that x is the number of Big Macs that a person consumes over a year, and then y is the cholesterol level of that person. Okay, so what we want to do here is that we want to fit a line through the scatter plot that approximates the linear trend of the scatter plot. Now you may ask, why do we want to fit a trend line? So I'm going to call that a trend line. So the trend line is the line that approximates the linear trend of the scatter plot. So why do we want to fit such a trend line? Well, so the reason we want to do that is the following. So the trend line will allow us to predict the values of the response variable y for x values that are not in the data set. So here's what I mean by that. So let's say that x5 is a value of the explanatory variable. That is so for us, let's say that x5 is the number of Big Macs that wasn't in our data set. And so then I can find the corresponding y hat value from the equation of the trend line. So let's say that the corresponding y hat value that we obtain from the equation of the trend line is y5 hat. So then we are saying that, we're going to think of y5 hat as the predicted value of the response variable when the explanatory variable is equal to x5. So here we're saying that if the number of Big Macs is x5, then the corresponding cholesterol level is y5 hat found from the equation of the trend line. So then we can use y5 hat as a predicted value of y. Okay, so now you realize probably already that there are many straight lines that we can fit through our scatter plot, right? So there are just too many lines that we can fit through our scatter plot. So the question is, which one do we pick? So there are many lines that we may fit through the scatter plot. So which one is the best fit line? Well, the answer to that question depends on how we define the phrase best fit. So that's the first thing that I want to do, is what do we mean by the best fit line? To understand what we mean by the best fit line, the first thing we need to do is look at what we call residuals. So let's focus on the point x1, y1. So this is a data point, and I want to look at the distance from this data point to the fitted line. So let's say we have a fitted line given by this equation here. So I want to look at the distance from the data point x1, y1 to the fitted line. So what will that be? Well, for x1, the height of the fitted line is y1 hat. So y1 hat is the height of the fitted line at x1, and notice that y1 is the height of the data point x1, y1 from the horizontal axis. So y1 minus y1 hat would be the distance from the data point x1, y1 to the fitted line. This y1 minus y1 hat, this is called a residual, and this is the vertical distance from the data point to the fitted line. So to understand what we mean by the best fit line, we first look at the vertical distances from the data points to the fitted line. Again, these are called distances are called residuals, or also called errors. So here's again my scatter plot, where I have highlighted the residuals, or the vertical distances from the data points to the fitted line. Once again, so here y1 is the height of the data point from the horizontal axis, and y1 hat is the height of the fitted line from the horizontal axis. So y1 is the value of the response variable corresponding to the explanatory variable x1, and y1 hat is the predicted value of y from the found from the equation of the fitted line by plugging in x1. Similarly, here again, y2 is the value of y from the data set, and y2 hat is the value of y obtained from the equation of the fitted line when the x value is x2, and so on. So these are the errors, or these are the distances from the data points to the fitted line, and these are called residuals. So the residuals are y1 minus y1 hat, y2 minus y2 hat, y3 minus y3 hat, and y4 minus y4 hat. So the question then, and then now I'm ready to answer what do we mean by the best fit line. Well, the best fit line is the fitted line that minimizes the sum of the squared distances from the data points to the fitted line. Again, the best fit line is the fitted line, or is the trend line that minimizes the sum of the squared distances from the data points to the fitted line. So here I'm using a table to summarize the residuals. So these are the x values from our data set. These are the y values from our data set. And so then I'm computing the y values from the trend line equation corresponding to these x values. So these are the y1 hat, y2 hat, y3 hat, y4 hat. These are the values of y from the given by the equation of the trend line corresponding to the x values in the data set. And then these are in the last column I have the residuals. So these are the distances from the data point, vertical distances from the data points to the trend line. The least squares regression line is the following. So we want to pick b0, b1, and the line y hat equal to b0 plus b1x, such that the sum here of the squared residuals, or sum of the squared vertical distances from the data points to the fitted line is least possible. So here, this is the sum of the squared distances, and in short we use the summation notation sigma to denote this sum. So this is summation square of the errors, or we can write the summation I going from 1 to 4, because we have 4 data points, yi minus b0 plus b1 xi squared. So again, yi is a y value from the data set, and data set corresponding to the x value xi, and b0 plus b1 xi is the predicted y value from the trend line corresponding to xi. Okay, so again, this is a short notation for this big sum right here. So again, we want to pick a trend line y hat equal to b0 plus b1x that minimizes this sum. And so we want to pick the line that minimizes the sum of the squared distances from the line to the data points. Now, this problem can be solved by using calculus, and as a result, I won't be going over the details here, but let's just say that applying the magic of calculus, we obtain the following formulas for B0 and B1 that determines the equation of the trend line. So B1 turns out so the trend line that minimizes the sum of these square distances turns out is given by an equation y hat equal to b0 plus b1x, where b1 is r times sy over sx, where r is the correlation coefficient, sx and sy are the standard deviations of x and y. B0 is the mean of y minus b1 times the mean of x. All right, so like I said, this is our least squares regression line. So if we use B0 and B1 by using these formulas, that gives us the least squares regression line, and that's what we're going to use to predict the value of y for a given value of x that may not be in the data set. So here's an example. Let's say that here we have the scatter plot for number of beers and the blood alcohol level. And so let's say the least squares regression line turns out to be given by this equation. Y hat is equal to 0.0144x plus 0.0008. Now let's say that we want to know the blood alcohol level if a person drinks 6.5 bottles of beers, let's say. So now notice that 6.5 is not in our data set, so we use the trend line equation to predict the blood alcohol level. So in the equation of the trend line, we plug in 6.5 for x, and then we calculate the value of y hat. So we see that we get 0.0944, and that's the predicted value of the response variable here, the blood alcohol level, when the number of beers is 6.5. I want to point out that so y bar here denotes the mean of y, the response variable y, and what I want to show here is that the mean of y hat is also the same as y bar. So y hat, recall, is given by b0 plus b1x. So the mean of y hat, so y hat bar, that's the mean of y hat, that's equal to b0 plus b1 times the mean of x. And notice that this is exactly the same as the mean of y, because that's what we get from the formula for b0. So recall from the formula for b0 here. So here we can, if we solve for y bar, then we will be getting b0 plus b1x bar. So we get y bar is b0 plus b1x bar, and so notice that that's what I'm using here. Y bar is b0 plus b1x bar. So that tells you that the mean of y hat is the same as mean of y. All right, so now what I want to look at is how much of the variation of y is explained by x. So how much of the variation of the response variable is explained by the explanatory variable. So first look at the idealized version here. So if all the data points fall on the trend line or the regression line, okay, so if all the data points fall on a line, then that line is the same as the trend line or the regression line. So in this case, the response variable y is completely explained by the explanatory variable x, because we can give a formula for y in terms of x. So we can predict the value of y exactly by using the value of x. Now, so we're going to think of the regression line as the best way the explanatory variable x explains the response variable y. So again, the regression line is the best way the explanatory variable x explains the response variable y. The question is how much of the total variation, or what percentage of the total variation of y can be explained by x via the regression line. To do that, let's look at one variation of y. So a variation of y means it's the distance of a y value from the mean of the y So y minus y bar is the variation of y from the mean. So that is, I can rewrite that as y minus y hat plus y hat minus y bar. So notice that here I am expressing the variation of y from the mean as the sum of two terms, where the first term, y minus y hat, that this variation is not explained by x, whereas y hat minus y bar is the amount of variation that is explained by x, because remember that y hat is completely explained by x. So the total variation of y is the sum of the squared variations, where the sum goes over all the values of y, and that is the same as the number of data points, the size of the data times the variance of y. So the size of the data times the variance of y. So in our case, we took 4 data points, so started with 4. So the size of the data times the variance of y would be equal to the total variation of y. On the other hand, the total variation of y hat is given by the data size times the variance of y hat, and the variance of y hat means the variance of b0 plus b1x, because y hat is equal to this, and the variance of b0 plus b1x is the same as b1 squared times the variance of x. And the total variation of y hat is completely explained by x, again, because we have a direct formula of y hat in terms of x. So the percentage of variation of y that is explained by x via the regression line is given by this formula. So the numerator here is the total variation of y hat that we have seen here, and the denominator is the total variation of y. So again, the numerator is the variation of y hat, the denominator is the variation of y. Now I'm not multiplying by the data size here because they cancel out. And it turns out that this ratio is equal to the square of the correlation coefficient R. And the reason is, recall that the formula for B1 from the regression line we got was B1 is R times Sy over Sx. So if I solve for R, we get B1 Sx over Sy. So R squared would be this ratio. And so R squared is known as the coefficient of determination. And let me explain this using an example again. So let's say we are looking at the number of beers and the blood alcohol level. And in this case, let's say that the value of correlation coefficient R is 0.87, and so the R squared is 0.76. So then we can say that 76% of the variation of Y is explained by changes in X. 76% of the variation of Y is explained by changes in X. So if we have a scatter plot that looks like this, so here we have all the data points align on the line, right? In this case, 100% of the variation of Y is explained by changes in X. And in the second picture, notice that Y doesn't change at all when X changes. So 0% of the variation of Y is explained by changes in X. Here are the TI-84 instructions for computing the correlation coefficient and the linear regression line. And here is the TI-84 instructions for fitting a regression line through a scatter plot. Okay, so thank you for watching, and I will see you in the next video.